Hello, everybody. This is the video lecture to accompany section 15.1. We're going to do a chapter about water and aqueous solutions, and that's really the whole unit because chapter 16 is also relating to solutions. And so water is going to be the focus here. So we'll start with a joke about water. If H2O is water, then what is H2O for? Well, you know, stuff like drinking and bathing and washing your clothes. Yeah. There's the objectives for 15.1. There's a lot of slides here and a lot of review, and some of this I'll go quickly through, but remember, pause the video if you come on to a slide that you think you have some information you should write down, or you need to read over it again, or need to look something up. Pause the video. That's the beauty of the video lectures. You can shut me up without even raising your hand. It's a beautiful thing. So some review about water molecules. Very small and simple molecule, H2O, and we learned about the polarity of the oxygen-hydrogen bonds in a water molecule, because oxygen is very electronegative, a very strong attraction for electrons, and hydrogen not so much. So when the oxygen and the hydrogen share a pair of electrons, the oxygen more or less keeps them for most of the time. So that and the shape of the water molecule, it is bent. The hydrogens are arranged 105 degrees apart from one another, account for the great polarity of water. And a lot of what we're going to talk about in this unit relates to the freaky nature of water. And it's freaky because it's this little tiny molecule with a very high polarity, and that gives it all of its interesting features, the characteristics that make water so important to life and to chemistry. So it's very polar, and that gives it this strong attraction, one molecule for another. The negative parts of one water molecule would be attracted to the positive parts of another, and that will explain a lot of water's freaky characteristics. And, wow, 2 jokes in one video lecture. Why do white bears dissolve in water? Because they're polar, of course. There's a nice picture of a water molecule showing the partially positive and partially negative bits. The delta, lowercase Greek delta, means partial, so the partial negative on the oxygen, the partial positives on the hydrogens, because they're not able to hold on to those shared electrons very tightly. And that gives an overall negative, partial negative charge to the oxygen side and partial positive charge to the hydrogen's side. And again, the shape of the molecule is important. We have what is, in a sense, very similar molecule with CO2. Oxygen, the red spheres here, carbon, the black one in the middle. And oxygen, again, much more electronegative than carbon, so individually, very polar bonds between the central carbon and the oxygen on either side. But because we have 2 oxygens pulling equally hard on the electrons of the whole CO2 molecule, and those 2 oxygens are arranged 180 degrees from each other on opposite sides, their pulls cancel each other out, and we wind up with a non-polar carbon dioxide molecule. Okay, so bent shape and superpolar covalent bonds in the molecule means that we have an overall polar molecule in H2O. And because of the nature of the polar bonds in water, we have the possibility for one of the 3 types of intermolecular forces that we learned about the strongest on average. Hydrogen bonding being able to occur between water molecules. And it is this strong hydrogen bonding, this very widespread hydrogen bonding throughout a sample of water that gives it its unique properties. It's very high surface tension, very low vapor pressure, which means it has a very high boiling point and melting point compared to most things that are tiny like water. And here's some pictures showing hydrogen bonding. The one on the left showing hydrogen bonding between the partial negative nitrogen of an ammonia molecule, NH3. Ammonia is also polar like water. And a hydrogen from a water molecule. More typically, we think about hydrogen bonding in water with water hydrogen bonding to other water molecules, which is obviously going to occur in every sample of water. And you can see that the positive hydrogens are arranged so that they're close to the negative oxygens of another molecule. And that little dotted line between these two molecules and the little dotted line here between these is those are the hydrogen bonds. And students miss questions on tests pretty frequently by describing the bond between the oxygen and the hydrogen on the water molecule as being a hydrogen bond. But it's not. That's just a covalent bond. The hydrogen bond is between the molecules. Hydrogen bonding gives water a skin-like quality that we call surface tension. And all liquids have this property, but water has it like to a freakish extent, to the extent where water molecules always are round, water droplets are always round. Now, if you get a big enough puddle of water, it flattens out because gravity will push down that spherical shape. But small drops of water are always round, and the skin-like quality of water will allow relatively lightweight things to stand on the surface of water. I love this picture. This is a coin dropping into some water, and you can see that the coin has created a little cave, a little tunnel in the water with air coming way down below the surface of the water, passing behind the coin. And this is that skin-like surface tension of water. I think that's an awesome picture. Here's something we'll do in class. Again, showing that skin-like surface of the water. It's a glass of water with a steel paper clip floating on the surface, but it's not really floating, because floating happens when we have something that is less dense floating on top of a more dense medium. Well, that paper clip made of stainless steel is about 5-6 times more dense than the water, and yet it's sitting on the top because of the surface tension. So there's the picture of the hydrogen bonding again, but we already saw that. Here we go with surface tension. When we have a sample of any liquid, there are attractions between the particles. And if we have water, we have strong attractions between the particles. So if we're down in the middle, like looking at this molecule in the very center of this diagram, there's going to be pulls, attractive forces, coming from all directions with water molecules all around it. And that's going to be true of all the molecules that are down in the middle of the sample of the liquid. But it's different on the surface. On the surface, there are no molecules pulling up. Let me get to my pen. There are no molecules with attractive forces pulling up against these molecules that are on the surface. Now, there's air molecules up here, nitrogen and oxygen, but they're not attracted to water because they're nonpolar. So the only thing that's pulling with the molecules on the surface are side-to-side pulling and the molecules pulling down. And so they tend to be more tightly packed and more tightly held together on the surface, and that is what creates the surface tension for any liquid. And because the attractions between molecules in water are very strong, surface tension for water is very strong. That rounded appearance of water is also a function of surface tension, and this attractive forces on the surface only being down and side to side. So that pull from all directions below the surface keeps a droplet of water in a spherical shape. And water doesn't always start off spherical when it's dropping off of something, but give it a second or two to free fall, and it will establish a nice spherical shape, like this droplet that's coming off of the faucet there. Surface tension also explains some of the things that we see in class. Surface tension and adhesive forces, sticky forces that water molecules have. Glass is made of silicon dioxide, which is polar, and so there's polar nature to glass, and so water molecules tend to be attracted to the molecules in glass. So if we have a container, like a graduated cylinder that's made of glass, the water molecules will stick to the surface of the glass, and at the water and air interface, there is only these attractive forces, nothing again, pulling the molecule this way, or this way, or this way. So we wind up with the molecules sort of being able to climb up the sides of the glass of a graduated cylinder or any other glass container that we might be carrying around water in. And this is what causes the meniscus that we've been looking at since the beginning of the year when we measure out something liquid into a graduated cylinder. We always measure the volume of the liquid based on the very bottom of that meniscus. If we have a plastic graduated cylinder, then you don't really see a meniscus because plastics are not polar. They tend to be nonpolar, and they may be described as non-wetting, but the idea is that water is polar and they're not, so the water isn't attracted to them. So in a plastic graduated cylinder, you get just a straight line across. Compare that to this thin glass tube. This looks like a volumetric. Thank you. Thank you, Maho. This looks like a volumetric flask, and the meniscus there just on the line, slightly above it. And the other tube that I threw in here on the right side of this picture is mercury, which is interesting because it makes a reverse meniscus, because the mercury atoms are so strongly attracted to each other and not nearly as attracted to the surface of the glass, and so they make a hump. And that's what it would look like with water in a plastic cylinder. You get sort of a reverse meniscus that way as well, because the water molecules are more attracted to each other than they are to the plastic, so they tend to bunch up. Not quite as dramatic as it looks like in that picture, but if you have a thin plastic graduated cylinder, you can see the effect. All right, so like I said before, all things have surface tension. This skin-like quality of a liquid at its surface, caused by the way the molecules interact with each other at the surface. And the surface tension of water is very strong, especially strong, and so sometimes we want to break that surface tension up to make water more wet. And we use substances called surfactants. Surfactants are surface active agents. It's a funny contraction of three words. And surfactants are things that can break the surface tension of a liquid. In other words, it can break some of the interactions between the molecules that are on the surface of a liquid, and it makes water spread out. It makes water wetter. It makes water less likely to stick to itself and more likely to stick to other things. and that is the wetting ability of a surfactant. Makes things easier to get wet. And that's what all soaps and detergents are. And the fact that we add detergent when we wash our clothes or wash our dishes is for this particular reason. It lets the water get in there into the food and the gunk that's on the dishes, or into the weaving of the fabric of our clothes. And when that water can get in there like that, then it can wash out the stuff that we want to clean off. So surfactants are things that can break some of that hydrogen bonding between the water molecules. Okay, low vapor pressure, that's the other big property of water that we wanted to talk about today. Water has a very low vapor pressure, especially for a molecule that's so tiny. Most small molecules have really weak attractions for each other. Not so for water. So we have these hydrogen bonds that are the strong attraction. And low vapor pressure means that water has a low tendency to vaporize. And we talked about vapor pressure in the last unit, so hopefully this is a bit of review. And that low vapor pressure is the reason we can have water sticking around at the temperatures and the pressures that we have here on the Earth. If water did not have such a low vapor pressure, we wouldn't have all of this stuff that's essential for life running around. The last thing we're going to talk about with properties of water is ice, that is water ice, solid form of water. And like everything else just about with water, its solid form is also a freak. Just about every other substance in the universe, as you cool it down, the particles move slower and slower on average, and they tend to get closer and closer together because their kinetic energy doesn't bump them apart as much. So as you cool a liquid, it gets more dense, and that's true for water until you get to about 4 degrees above water's freezing point. For every other liquid, they keep getting more and more dense, the particles closer and closer together, until they freeze into a solid, and then the solid is more dense than the liquid. So if you drop a piece of solid into the liquid form of the same substance, it will tend to sink to the bottom like a stone. But we know from experience that water ice, the solid form of water, doesn't sink. It floats. It's less dense. Everything else sinks in its liquid. But even though it's very common for us, we don't think about it being weird. Water ice floating is very, very weird. And it does that because of the hydrogen bonding, creating this very regular arrangement of the water molecules. In the crystal form of solid water, the hydrogens of one water molecule arrange in a very distinctive pattern with the oxygens of adjacent molecules, and it creates an open structure in the crystal form of water. The molecules spread out a little bit as they freeze from about 4 degrees Celsius cold water to the ice at 0 degrees C. And in arranging themselves into this very orderly pattern that we see in the diagram here, they spread themselves out. So you can see back, 3 layers deep here, the water molecules are all aligned up exactly the same, one after another. And the hydrogen bonds that exist between the adjacent water molecules are the force, the glue that's holding that solid together. So when we have water ice like this, we create these open spaces, these hexagonal, honeycomb-shaped open spaces in the structure of the crystalline ice. And that open space is nothing. So there's no matter in there. That means the whole piece of ice now has a bunch of empty space in it, and it makes it less dense than the liquid form of water. And you can imagine, and we've seen this video that I showed you guys in class. Ask me again if you haven't seen it. of when water ice melts. These water molecules that are now locked into these honeycomb arrangements can start filling in these spaces, and that's what causes liquid water to be more dense than solid water. About 10% difference between the density of ice and liquid water, and so the ice floats on the surface. That's important to life on Earth, like a lot of other qualities of water. A lot of places where life exists has very cold winters, and the large bodies of water, the seas and large lakes, will not freeze solid in the winter. A layer of ice will form at the top, floats on the top of that lake, and then acts sort of like an insulating blanket and keeps the liquid water unfrozen beneath it. And so the aquatic life that lives in those environments can survive the winter, whereas if they froze solid, it would be a little tougher. We learned in the last unit as well that there are energy changes associated with phase changes. When we change from ice, the lowest energy form, solid, into liquid water, melting, we have to add energy to the particles. And likewise, when we change from the liquid form to the gas form, we have to add more energy. It's a bigger jump energy-wise to go from liquid to gas, because gases have very much higher average kinetic energies and than the liquids or the solids do. So that's where the biggest jump is. And that's it for 15.1. And that's enough. Yeah.